All right, hi guys. So honors, this is your lecture on isotopes. We have briefly introduced isotopes already in class. If you are in Mr. Hufford's class or another teacher's class, I will be most likely your honors teacher. So yay. So with isotopes, don't forget that these are atoms of the same kind of element, just with a different mass number, a whole number, due to the change in the number of neutrons. You can never ever change the number of protons because you can't change the identity. All right. So that being said, let me quickly introduce how we communicate isotopes in the written language of science. So you have already looked at the periodic table and you've already looked at how it's written with the atomic number, proton number on top, and the average atomic mass or the relative atomic mass on bottom in AMU, atomic mass units, a very special unit that we use. Sorry, there are a couple students in my class right now. A very special unit that we use to scale down talking about mass and measurement. All right, so just as a quick review, we can quickly write relative or average atomic mass, all right, is the average, okay, mass of the various isotopes that exist for an element. So I think the original comparison I made in class was that if I had a bag of Skittles, not every single Skittle is actually manufactured to the minute exact mass. And if we were to weigh them, we would say, oh my goodness, if I were to pick up a Skittle randomly from a bag, what would its average mass be out of kind of almost like a statistical probability situation, all right? But mass number, though, is the specific mass of that mass of that one Skittle. And this is always protons plus neutrons. Okay, and here we are, of course, the only thing that we're really changing to get a different mass number is this is what changes for isotope. All right, and mass numbers are always whole numbers, always whole numbers. And a mass number is specific to the isotope. Okay, so we have a specific notation called isotope notation to convey this information. It is actually very similar to the periodic table, except for a couple things. We flip the information. Why? Because the most important information when we talk about an isotope is the mass number. The atomic number stays the same because we're talking about the same element. So give me 1 second. Okay, so let's take carbon, for example. If I were to write the isotope notation for carbon, okay, and here's some possible carbon isotopes that exist out there. Carbon 14, carbon 15, carbon 12, and carbon 13. If I were to write the isotope notation for, let's say, carbon 14, all right, I would actually put the mass on top. I'd put 14, okay? And of course, we know it's an AMU. I'd put the atomic mass number on top, and then I would put the Z, the proton number, on bottom, which is 6, okay? And this is what's shared. The element symbol and the atomic number is shared. What changes, though, is the order and the type of mass that we represent. So this is our proton number Z. So this would be isotope notation. Now, quickly, what is this notation that I just wrote? This shorthand of all these various isotopes of carbon. We call this isotope name notation, where we write the name of the element or the symbol, and with a dash, we specify its mass number. Again, because what we care about with isotopes is the change in neutron count, which therefore changes the whole number mass number, all right? So that's just like your quick review as well as notation. You will be expected to write and interpret between these 3 types of notations, okay? So here's some examples. Feel free to study this. Quick note, here is your mass number on top, the thing that changes between these 2 isotopes of hydrogen, and your proton number, atomic number on bottom, which is consistent because it's the same element. All right, so let's talk a little bit about the math behind isotopes. How do we exactly calculate average atomic mass? Well, first term that you need to know is isotope abundance, and this is the amount usually represented in percent that an isotope contributes. Okay, another way of putting it is it's the percent of existence in the world. Like, how likely are we going to get this? All right, so it's pretty simple math, and I'm only going to walk through one example, and then I'm going to leave the rest for you guys to do because you all are honors, and I assume most of you have had algebra before this. So carbon, let's say I have these 3 isotopes. Okay, this is my sample. I would say to myself, well, I know that carbon 13 with a mass of 13 AMU contributes about 63%. Change that to a decimal so I can actually do the math, and it becomes 13 times 0.63, which is equal to 8.19 AMU. I also know that carbon 14 with a mass of AMU contributes about 14% or 0.14% of all the isotopes of carbon out there. This is equal to about 1.96 AMU. And of course, then we have carbon 15 with the mass number of 15 AMU, and it contributes about 23%, which in decimal form is 0.23. This is equal to about 3.45 AMU. If I took all of this and said in the whole world, I am most likely to find a carbon with an average mass of the sum of these contributions, the sum of these percents abundance of isotopes. And I would get a value of about 13.6 AMU. Now in the periodic table, we often go to the second decimal, right? But here, just due to my math values, I'm going to the first. But the big idea is that you can do this math and notice something. Okay, when you look at the isotope in greatest abundance, you'll often notice that it has a mass number closest to the average atomic mass reported on the periodic table. Why? Because it's the most dominant presence. It has the greatest abundance. It kind of dominates and affects and shifts the average weight more toward itself. So go ahead and work through example 2 and 3 on your own, and hopefully we'll get an opportunity to talk about it and compare with a classmate. But best of luck, everyone. And we're in our first weeks. So I'm really hoping that as you consider whether or not to continue on with the honors track, that you are inspired to test yourself to a higher level. So bye, guys.